So we're already very familiar with linear functionals. A linear functional on a vector space V is just an element of the dual space. That is, it's a linear transformation from V back to the field. And sometimes, especially in this section, we'll use a Greek letter to denote an element of V star, to denote one of these linear functionals, and a V, and a Roman letter to denote the vector. Now, in the presence of an inner product space, in the presence of an inner product, we have a very nice way to define a whole collection of linear functionals. The map inner product with V, this is blank, plug whatever in there, which I could think of as a map that takes an element of the vector space and spits out an element of the field. That's a linear functional, because we know the inner product is linear in the first coordinate, right? If I left the second one blank, it would be a conjugate linear, but almost linear. Is a linear functional. So defines a map, defines the element of V star. Right? Inner product with V is in V star, another way of saying that. And so this is kind of that promised way to associate to each vector in V an element of V star in a way that requires no further choices once I have an inner product. Another way of saying this is that the map that sends U to inner product of U and V is the linear functional. If you're uncomfortable with the blank, this is what that means. So every element of the vector space V gives rise to a linear functional this way. And the surprising thing is that in the other direction it works. That is, every linear functional, every element of V dual can be expressed as inner product with something, or can be represented as an inner product with something. That's a theorem. Doesn't have a name in your book, but it's called, in general, the Riesz representation theorem. This is something that shows up in a much more general context, but we only really need the finite dimensional sort of simple version of it. But there are many such representability theorems. And what it says is this: for all linear functionals, which I'll write phi, in V star, so for all elements in V star, there exists a vector V in ordinary V such that phi is equal to this function inner product with V, i.e. for all other vectors U and V exists a phi of U is equal to the inner product of U and V. So for every linear functional exists a unique, it's important, there exists a unique vector V and V that represents it in this way. So to prove it, we want to first prove that such a thing exists, and then we'll show why it's unique. So to prove it exists, that is, there is such a V that represents it. Let Let's choose an orthonormal basis. V is an inner product space. We've talked about how we can construct an orthonormal basis. That makes thinking about decompositions in terms of the basis easy. So let's let U be an arbitrary element of V. And we'll write U in terms of the orthonormal basis as the sum of the coefficients times the basis elements, and the coefficients are the inner product of U and the basis element. That's how we express anything as a linear combination of orthonormal basis elements. Applying phi to this U, this is the thing we want to represent as an inner product. We get phi of this whole expression. Phi is a linear functional. Being linear, I can push it through the sum. Right, so this is equal to phi of this sum. And it's also equal to the sum from I equals 1 to n, U ei. The only vector left in here is ei, right? Phi of ei. Find now phi of ei. Phi is a linear functional, so, and this is a vector, so phi of ei is just a scalar, right? So everything here is a scalar. This is a scalar, and that's a scalar. But we want to get on the right-hand side an inner product. So we want to sort of consolidate this expression, which is a sum of inner products and this, into one big inner product. First thing we want to do is to take this guy, phi of ei, and move it over there. Because the inner product is conjugate linear in its second slot, moving phi of ei into here means I have to conjugate that. Take its complex conjugate. So that's U phi of ei conjugate times ei. And now I'd like to consolidate the sum. Well, we know that the inner product is linear in the first coordinate and conjugate linear in the second coordinate. So I can actually pull this U out and apply the sum to the second part. Right? So this is equal to the inner product of U with the sum from I equals 1 up to n, phi of ei bar ei. So I've succeeded in writing it as a giant inner product. U is unchanged, and the thing that it's being combined with in the inner product is the V that we were looking for to represent our linear functional phi. So that's our answer. So that shows that it exists, that there is such a V, that phi of U equals U V. And now we just need to show that this V is unique. So for that, suppose I have two vectors which work just as well to represent. That is, given any other vector U, phi applied to U is the same as taking the inner product with V1, and also the same as taking the inner product with this V2, the second solution to this problem. Of course, you want to prove something is unique. Very often you need to subtract. So subtracting one of these from the other, I get that 0 is equal to the inner product of U with V1 minus the inner product of U with V2. And by linearity, or additivity in the second slot, that's the inner product of U with V1 minus V2. So now we seem a little bit stuck. We want to show that this is 0. But this is, so this statement, this equality has to hold for every possible u. So if I set, I'm allowed to choose u to be itself v1 minus v2. Then the requirement that this is 0 tells me that after setting that, I get v1 minus v2. v1 minus v2 is equal to 0. v1 minus v2, v1 minus v2 is equal to 0. And so it must be that v1 minus v2 is in fact the 0 vector. And so v1 equals v2. And in fact, there was only one such thing. Okay. So now I want to talk about this concept of adjoint. So adjoint is a little bit of a confusing idea. I'm going to try to explain it in a couple of different ways in the hopes that at least one of them will make sense to you. So suppose we have a linear transformation from one vector space to another. We're looking for ways of getting a map that goes in the other direction. Right? So one of those was on your exam, but we're looking for, we might be interested in finding ways to get a map that goes in the other direction in some kind of canonical way. To draw a picture, one of the ways to do that is, so think about F as being a matrix, right? If I have, I've chosen a basis for V and W, I have a matrix, and I can think about F as being, say, from Rn to Rm, right? It's easy to get a map that goes in the other direction from Rm to Rn by just taking the transpose of the matrix, right? That's going to be not quite the right answer, because when you're really careful about that, that is actually a map, let's call it F transpose, which goes from, not from W, but from W star to V star. So the invariant thing that's happening is that, what does this mean? It means if I have a linear functional omega here, I can get out a linear functional, say, nu over here. And how does that work? Well, a linear functional, an element of V star, is just a function that eats something from V and spits out something from the field. How do I obtain that from the data of F and a linear functional on W? Well, I just apply F to V, and then I apply the linear functional to that. Right? And that's my linear functional. The linear functional, this is supposed to be omega, this linear functional. So first I take V, I translate it into something which is in W, and then I apply my linear functional, and that gets me a field element. And so that composition provides a map from V to F. However, it doesn't really go from W to V, it goes from W star to V star. The picture for that is if I have a linear transformation F, it goes from V to W. This transpose, what's happening here are all these evaluation maps. So what I'm really doing is I'm bending these wires around, applying these evaluation maps, and what I get out is this one is labeled W, this one is labeled V. I get out, the wire here is pointing in the wrong direction. So I get out a big box, which has as its input W star, W dual, and its output is V star. So this is this F transpose from W star to V star. That's not quite what we want. What we're looking for now is a map that actually goes from W to V. And this is something different, which is the adjoint. In matrix land, it would be the conjugate transpose instead of just the transpose, if I have the usual dot product, inner product. I don't expect this to make sense yet, but I'm trying to give you sort of different points of view on it. OK. So let's say this another way. Suppose I have, so there's not enough data yet. Until I get an inner product, there's not enough data to construct a map that goes from W to V. But now suppose V and W have inner products. Now I have more structure, because I have this ability to turn a vector into a dual thing by just taking the map inner product with me. And there's something more I can do. So again, let F be a linear map from V to W. And I want to fix some W in W. And I want to consider, I have a composition. First I take V, I apply F, and I get F of V. And then I apply inner product with W, and I get F of V W. So I have a composition of two linear maps, F and inner product with W. And this goes from V to W to the field. And the idea is that this inner product here is being taken in W. Right? F of V W. I'm taking it, I have two vectors, V and F. I have one map, and I have an inner product. The inner product is taking place in W. We're looking for a way to convert this inner product to an inner product that happens in V, kind of pull it back in time and look at it on the other side of the transformation. So we're looking for some G such that I can take G of W and the original vector V and take the inner product in V and get the same answer. So G would be a linear transformation from W to V. And this would be an honest transformation without the stars that goes in the other direction. And sort of allows me to translate my inner products between these two languages, the inner product in the space V and the inner product in the space W. So such a thing does exist, and such a function G does exist and is linear. It's called the adjoint of F. Such a G exists. It's called the adjoint of the linear transformation F. And it's denoted F star, or sometimes F dagger. So somewhat confusingly, some people use star for this map and dagger for this map. In this book, in this class, we'll use star for the adjoint, and we will mostly not concern ourselves with the transpose. This is supposed to be a dagger. Okay, so the way of stating this as a theorem, suppose I have V and W inner product spaces over the reals or complex numbers, and let F be a linear transformation from V to W. Then there exists a unique, E exclamation, backwards E exclamation point means exists unique. There exists a unique F adjoint, which is a map in the other direction, such that it solves this equation here, FV. So this has a solution. The inner product of F of V and W taken in W is equal to the inner product of V and this F star applied to W taken in V. Proof. So the idea is we have this map gamma. It sends W to phi of FW, where phi of FW is this map sending V to inner product with f of V with W. So it takes the data of a map F and a W, applies it to a vector space V, and spits out a scalar element. So let's see, this is in V star. So gamma goes from W to V star. And then we have this other map sitting around R for Riesz, the Riesz map, which takes V star to V. I explained it in the other direction, but I can think about it as going either way. And so combining these maps, I get a map from W to V star, this one, called gamma, and another map from W's V star to V, called R. Now, neither of these maps are actually linear, if you think about it, because this one shows up in the second element here, and similarly for the Riesz map. However, they're both conjugate linear. So they're both linear, are linear, and then take the conjugate. And so when I combine them, I've taken the conjugate twice, and I have a linear map. So F star, which is the composition of these two maps, are composed with gamma, because gamma is where the original F shows up, is linear, and goes from W to V. Okay, so there's a lot of indirection going on here. The maps viewed as vectors and things like that. So we're going to sort of talk about it in a couple of different ways. Another way to say that, and then I'll stop and we can discuss things from the midterm a little bit. Another way to say that is the following. I have this map that takes V to f of V to f of VW. This is a linear functional because it's linear, it eats V, it spits out something in the field. And then we just define, not as a linear map, but as a function, define just the function f star by f star of W is the unique vector in V such that the linear functional above, this one, is represented by inner product with f star of W. We knew that such a representation exists by that Riesz representation theorem. So such a thing exists, and we're just defining the function f star of W is equal to that. We show it exists, and then we just need to show it's linear. So this way, we got something which was linear automatically. This way, we have to show it's linear, because we just defined it to be a function. So that is, it's an element of the vector space L of linear transformations from W to V.